So we are continuing on in our discussion of the kind of the cause of the radiation reaction, and we're using this model where we have a dumbbell of charge separated by a distance d, um, where the charge has been divided up into Q1 and Q2, which we now assume to be of equal magnitude. And this dumbbell is moving in the x direction, and the goal is to then eventually take the limit of the separation of the charges down to 0. So where we left off in the last lecture was we wrote down the electric field for charge number 1, and now what we can do is we can now start putting in some of the parameters. So the velocity u is just c(r) minus v, where we assume that v is equal to 0, so it's initially at rest. So that means u is c times r. R is a vector which you can write as L in the x direction plus D in the y direction. So going back to our picture, the radiation, basically, the field basically traveled a distance L in the x direction and D in the y direction. Okay, that means R dot U is going to be equal to CR, and R dot A is going to be equal to L times A, and R is the square root of L squared plus D squared. So that's good. So now we're rewriting all of our equation in terms of R's, L's, and D's. Now we're only really concerned with the electric field in the x direction. So the electric field in the y direction is now responsible for binding the two charges together. And eventually what we're going to do is we're going to take that distance d down to 0. And so in the end, the electric field in the y direction doesn't contribute to what I would say is the radiation. We're only looking at the electric field component that's in the x direction. Okay, so therefore, the component u in the x direction would be c times L over r. We get that from our triangle. And so now if we put all this together, the electric field from charge number 1 in the x direction is q over 2 over 4 pi epsilon naught square root L squared plus D squared over CR cubed times C squared plus LA times CL over R minus CRA. So we can clean this up a little bit. And one thing we know is that the square root of L squared over D squared, that's really R. We can factor out a C over R out of each of these terms. And when we do that, I can then cancel this R with one of the R's down here and get a C cubed R squared. So let's rewrite this now as Q over 8 pi epsilon naught 1 over C cubed R squared C over R C squared plus LA times L minus R squared A. Okay, now I can cancel one of these C's and multiply the R's together, and I get Q over 8 pi epsilon naught 1 over C squared R cubed And then I can multiply the parentheses out. So I get c squared L plus L squared A minus R squared times A. Okay, so now what I want to do is try and clean up what's inside the square brackets. So I can do that by essentially writing out an L squared A. Okay, so I'll write this out as Q over 8 pi epsilon naught 1 over c squared r cubed c squared times L and plus L squared A plus a minus L squared A minus dA squared. Okay, so basically what I did was I took the r squared right here and rewrote it in terms of L squared plus D squared. Okay, so now that allows me to do some factoring, and what I get is Q over 8 pi epsilon naught c squared and then I get L c squared minus A d squared over R cubed times R, which I can now rewrite as, no, I'm sorry. Anyway, if you combine the R cubed and the factor that you need to make the squares in the numerator, what you get is essentially R to the 3/2 power, which I can now rewrite as L squared and D squared to the 3/2 power. Okay, so by symmetry, the electric field on the second charge is the same thing as the electric field on the first charge because I've broken them up into equal magnitude charges, and it's a very symmetric case, moving at the same, they're basically positioned at the same distance away from the x-axis. So therefore the net force, which I'm going to call self, so basically the self interaction between these two charges is Q over 2 electric field 1 plus electric field 2. So there's a force of 1 acting on 2 and the force of charge 2 acting on charge 1. So if that's the case, what I get is Q squared over 16, oh no, I'm sorry. So essentially E1 and E2 are the same, so that would be 2 times the electric field equation right here. So that 2 cancels with the 1/2, and I get Q squared over 8 pi epsilon naught C squared L C squared minus A D squared over L squared plus D squared to the 3/2 power in the x direction, because I defined it moving in the x direction. Okay, so now what we want to do is take the approximation where d goes to 0. Okay, so to do this, instead of just saying d goes to 0, why don't we write out things in a Taylor expansion? So x at the initial time, I'm sorry, x at the time measured now is equal to x at the initial time plus the derivative of x at the initial time times the time difference plus 1/2 the second derivative of the position taken at the initial time times the time difference squared plus 1/3 factorial, the third derivative evaluated at the initial time times that time difference cubed, and so forth and so on. Okay, so we could keep going on and adding more terms. And so I said that we wanted to start at an initial velocity of 0. So that means that x dot is equal to 0. So that eliminates this term right here. And I'm going to let my time difference, I'm just going to call that capital T, so it's much easier to write out. And when I do that, the length L is just x t minus x at the initial time. Okay, so therefore I can subtract out this term and bring it over to this side and make it into an L. Okay, so if I do that, what I am left with then is L is equal to 1/2 a t squared plus 1/6 the first derivative of the acceleration with respect to time, t cubed plus dot dot dot. Okay. So I think I'm going to stop right here, and then I will finish this derivation in the next video.